Okay, I see three people who push the answers. So I think it would be okay to start screen sharing, and we will discuss all of these questions from the first one. Do you see my screen?
Yes.
Yeah, okay. So the first question was if you work with neural machine translation problem using the sequence-to-sequence encoder-decoder architecture, what can we use? So by the way, all the answers are correct, and we can choose all the answers. I will explain why we can do it. So the first one was about RNNs in the decoder part. So recurrent neural networks are commonly used as decoders in sequence-to-sequence architectures. So because of this, we can effectively handle sequential data, making them suitable for generation translations via RNNs. The second one was about convolutional networks, and we can use it in encoder part. Particularly is in machine learning, in machine translation. We use it sometimes because they are capable of capturing hierarchical structures in the input text. So we can do this. And the third option was about convolution networks in decoder parts. We don't, okay, it is technically possible, but we don't use them much in this part. They can generate output sequences by using positional encodings and causal convolutions. So we can say that it is possible, but we don't do it usually. And the last one was about RNNs in encoders part. In sequence-to-sequence models, since they are good, we use it since they are good at processing sequences and learning contextual information from the input text. So do you have questions why all the options was correct in this context? Okay, if not, we will discuss second question. It was about perplexity score, and correct answer was compared to models and one translation task. And why do we can do why we can choose this option. Perplexity is a metric used to evaluate the performance of language models. We discussed that on previous lesson. And in the context of machine translation, it helps compare how well two models predict the sequence of words within the same translation task. A lower perplexity score indicates that the model is more confident in its predictions. So, and third question was about perplexity 2. Here we can say that the perplexity score doesn't need the human writing translation of the selected text. We can say this because perplexity is measure of how well a model predicts a sequence of words, and it is calculated based on the probabilities assigned by the model itself. It doesn't require a reference translation. I like blue score, and Next question is about blue score. Here we have two options, and we can say that it needs the human written translation of the selected text. So we can say in this way because blue score is a metric used to evaluate the quality of machine translated text by comparing it to a human written reference. And the score indicates how closely the machine generated translation matches the reference translation. Okay, maybe I'm too quickly going through all the questions. Do have some issues, or maybe you didn't get something, or maybe do you have questions? Okay, so next question would be about select all the correct statements. Here we can say that correct answer is without normalizing. Yeah, without normalizing scores, long hypotheses would get lower scores than the short ones. Like we can say that it is correct on option when using methods like beam search for generating sentences. 1 second. Yeah, okay. So yeah, why we are using this, a longer hypotheses tend to have a higher chance of accumulating lower probabilities, since the score is calculated as a product of individual token probabilities. And numerization helps balance this bias towards shorter sentences. And second option was about beam search. The beam search may choose only between predicted sentences of the same length. This statement is incorrect because beam search can generate sentences of different lengths. It doesn't restrict the search to sentences of the same length. So, and last question was a little bit funny because it's rely on historical information, but okay. The correct answer was about Cold War. The development of machine translation was driven by the need to automate the translation of Russian text into English during the Cold War era. The goal was to facilitate communication and intelligence analysis between the US and USSR. Okay, maybe some more questions. Maybe we didn't discuss some parts, and you have other questions about this. Okay, so if you don't, today we will discuss attention mechanism. It is, I think, it is a very important topic, and we will have not one lesson about attention, but as you can see, we have two notebooks today. But this notebook, it's like an extra lesson, and maybe we will discuss it next time. Maybe we will have time today, and if we will hurry up, or I don't know. Yeah, we have a huge schedule for today's lesson. And so I don't know, will we have time today for this notebook, but it's really important to understand this mechanism, because today state-of-the-art architectures, they rely on attention mechanism, and a lot of experiments in research area, they show that if we will not use it, we will have lower metrics in all benchmarks that we have. For example, for large language models, what we will discuss at the end of our course. Yeah, so, and it is heavy mechanism. I mean, it's heavy by it's computational. Yeah, and because of time that we spent on this part of our architectures. But today, research areas, it is a lot of, I mean that it is a lot of works about how to do it more optimized, how to do it lighter in today's architectures and not lose metrics in the same time. So, okay, I think I discussed with you that it's very, very important to understand all of parts of today today lesson, and we can start with first notebook. As you can see, here we have sequence-to-sequence models. We had it on previous lesson, but I think we will refresh a little bit our knowledges. Also, you have homeworks with like second homework with this technique, and it would be nice, okay, to tell all of the information second time. Okay, sequence-to-sequence models are widely used for tasks that involve transforming one sequence into another, such as machine translation, where a sentence in one language is converted into its equivalent in another language. For example, if we discuss machine translation. Encoder-decoder architecture, the traditional sequence-to-sequence model, they consist of this architecture. Processes the encoder parts processes the input sequence and compress it into a fixed size context vector. And decoder part uses this context vector to generate the target sequence one word at a time. Okay, we have problem, I think, with sequence-to-sequence. Major issue with this basic architecture is that the entire input sequence needs to be summarized into a single fixed size context vector, which can lead to a loss of information, especially for long sequences. And the attention mechanism addresses the issues, this issue by allowing the decoder to focus on different parts of input sequence at each decoding step. It computes a weighted combination of the encoder's hidden states, guiding the decoder to focus on the most relevant words from the input sentence when generating each word in the output sequence. So we will discuss attention mechanism a lot of times today, and I think you will get all of the information. I will start with explanation what we have in the beginning of this notebook, and we will discuss step by step what's going here. So I will have GPU today. We can run the first part of code. And I will explain what we have in the first part. We import essential libraries such as PyTorch here, such as, oh my God, okay. We will we will wait, yeah, via error, and then I okay, I wrote you how to fix this issue. We need to install. So right now, I think it would be okay. Yes. So let's move to the part where we stopped. Okay, we import PyTorch, we import NumPy and Torch text. Yeah. To handle data operations, neural network slurs, and text processing. Then we can set. What's wrong? It worked. I promise you. Here we can set seed. Do you remember why? Okay. Why we set seed? Can you answer me this question? Okay, all right. Anybody? Why we setting a random seed? Okay, so we set a seed value for random number generators to ensure that our results are reproducible. This means that every time we run the code, we will get the same results, which is crucial for debugging and comparing model performance. Is it clear for you? I hope that you can hear me. Can you?
Yes.
Okay, is it clear all what I said?
Yep.
Okay, nice. Okay, why doesn't it work? Um, mhm. Maybe it is not code of this year, and sometimes some code parts they can be a little bit. Um, 1 second. It can be not for our okay number of the version that we loaded. In this case, sometimes it could be issues like this, and think it would work for us. And in this case, we should search about the information what is right now, what is useful for number of this version. So I think right now it would work for us. Maybe we'll type like this and English core. Okay, nice. I hope that it wouldn't be a problem for further code parts, but if it would be, we will try to create some modification of our code notebook and try to realize the correct operations. Okay, so here we have tokenization and we load space models. We use spacey library for text tokenization. You should remember why do we need this library, because we had it in recurrent neural networks, and when we used CNNs for produced our sequential text, I mean sequential data. Okay, and we break down the text into individual tokens. Tokenization is the first step in processing natural language data before feeding it to a neural network. I always repeat it, but maybe it would be refresh your knowledges, and you will remember it in the future. And when we will have them, you will remember it too. So then we loaded German and English language models from space to handle tokenization in both languages. This step is crucial because our dataset contains bilingual text data. Then we have this part of code with EOS tokens and others. The field class from touch text is used to define how the data should be processed. We specifies that the text should be tokenized, converted to a lowercase. We pass it through this flag, and paired it with sequential tokens like this one, SOS, start of the sentence, and EOS, like end of a sentence. Also, we use multitask, multi-tree. Oh my god. Okay, we rewrite code for what's wrong? We write code in the beginning. Because of this, sometimes I think we would have some issues. Okay, can we not lose our time today, because it's a huge material that we need to discuss, and it's not the main part of our code notebook. I will rewrite all of this code, and I will create a branch for our year. I said you that in the chat, in the Telegram chat on weekends, but I didn't have time on Monday and Tuesday. So I hope I will do it tomorrow or maybe on Thursday, and then I will provide all the correct code seminars in that branch, and you will have good okay, code without issues. Yeah, let's just move to this code part, I will explain you why do we need build vocabularies. We create vocabularies for both the source German and target language, it's English in our case, using the training data. Words that appear less frequently than a specified threshold. Here it's two are excluded to keep the vocabulary size manageable. We had it on the previous seminar, and you need to remember this information, but I will tell you this second time. And vocabulary maps each word to unique index, which the model uses to look up words during training and inference. And then we have here some code parts with device that we can use. We check if a GPU is available and use it for computations to speed up training. If GPU is not available, we fall back to the CPU. Also, we have here this specialized iterator groups sentences. It's here of similar lengths into the same batch. This reduces the amount of pattern required and speeds up training by ensuring that all sequences in a batch are roughly the same length. With that data prepared, we now move to constructing the core components of sequence-to-sequence model. We did it on previous lesson, but today we will have attention mechanism in our architecture. But we will start with encoder, and it wouldn't be changes since previous lessons. We have here embedding layer. You can see it here. It converts the input words indexes into dense vector representations known as embeddings. These embeddings capture the semantic meaning of the words. Also, we have here GRU. Okay, did you met this lawyer previous? Do you know what's the difference between GRU and LSTM? Because we worked with LSTM on previous lessons, and I think we didn't met this.
No.
Okay, it's like a modification of LSTM lawyer. You can search for it in the Google. For example, I will type changes LSTM or something like this. Yeah, and so here you can see what's going on. Why it's have some modifications from LSTM. Here we can see this GRU that doesn't have an output gate. It's look like it. So I don't know. Did you have this on lectures? But if you want to understand all the details, you can go in through these images and see what's modifications we have. I don't know why it's don't load my image, but okay. So to be honest, I don't remember from just in the moment from the head what's difference between LSTM and GRU. It's kind of similar similar techniques, but they have okay, in the GRU there is output gate. I mean that this GRU doesn't have an output gate, and all of modifications with the LSTMs and GRU, they released because of long, okay, when we have long sequence, we can forget something. And so in this case, we should understand what should we remember in our memory, or what information should we lose. And because of this, LSTM and GRU, they created from RNNs. Is it clear? Did you have this information on the lectures or not?
I think we have it on machine learning course before.
No, you on machine learning course they don't usually they don't go in through gated recurrent units, because it's kind of technique just for language, or not only for text, but we can process with it maybe sound or another sequential informations. But sometimes I don't really know. But on the machine learning, like classic machine learning, sometimes I mean usually they don't go deeper to these details. But I don't know. Okay, so. Do you have questions about gated recurrent unit? Okay, here we pass bidirectional flag with, like, I mean, we pass it true. It's mean that it processes the input sequence in both forward and backward directions. I'm sorry. This allows the model to gather context from both preceded, I mean, both sides. And also we have outputs and hidden states from GRU at each time step, which will be used by the attention mechanism. And the final hidden state that summarizes the encoded information, which will be passed to the decoder part. It's all of information that we discussed is here. Do you have some more question about encoder part, encoder class? If you don't, we can move to attention, the main part of our lesson. So here we implement the attention mechanism, which helps the decoder focus on different parts of input sequence during the decoding process. I will explain what we have here in the code implementation, and then I will tell you, I think the easiest way to understand meaning of attention. I always, when I tell people how to understand attention mechanism, I always tell this, I don't know, like a similar representation of it. And I hope that it would help you to understand all of information that we discuss right now. So, okay, here in the code, we have attention calculation. The attention mechanism computes a score called, okay, a score that represents how relevant each encoder hidden state is to current decoder state. Also, we have here softmax. Where is it, by the way? Yeah, okay, it's in the end. Softmax normalization, the energy scores and normalized using a softmax function to get attention weights, which indicate how much focus should be placed on each word in the input sequence. These attention weights help the decoder decide which part of the input sequence to which part of input sequence is emphasized when generating each word in the target sequence. And now I will tell you how to understand it in the similar way. So let's imagine that we have a sequence right now. Let's imagine that it's text. It's not important. And we need to analyze on each step which information in this input sequence is relevant for our part where we are standing. Did you imagine this, or should I maybe provide some information with visualization? I will try to do it. So, for example, we have sequence here, and on each step, for example, I will show you with another symbol that we are on the current step, for example, with a star. So we are going through this sequence, and the star, it provides information where we are standing in the moment. So on the all the steps, I need to understand my current position, how it's close on the meaning with another sequence. Maybe when I'm standing here, the information is relevant on this part. I will provide with another symbol, and on these steps, and maybe on this. But all the other information, it's not important for me right now, and I don't need to analyze it because it would be not important for me to create my decision right now. And okay, I want to say you why should I rely my attention on this part if it's not important for me at this moment. For example, when I will move on the other step and I would be on the next position, it would be important for me this part, maybe this one, and maybe this. And why should I lose my attention on this part that are not relevant for me? Did you get my my example? If you are, I will say you how to calculate attention in the previous, yeah, how to calculate it in the architectures that are popular right now. Did you understand? Please give me feedback.
Yes.
Okay, so I would have, give me a second, I will analyze how you calculate attention here. Linear tensor, encoder, decoder. Okay, I will provide you information to how to analyze, how to understand this part. Maybe when we are going further, when we will move to more like it's okay. Here we have the easiest way how can we implement it. Maybe when we will go to the more difficult operation, we will discuss it not in the simplest way. When we are standing on the each part, we should analyze our position, and we will have a matrix for our position with all our embeddings. Okay, it's similar way how to understand how I tell you this information, but you should understand. And we need have two more metrics for other positions and just multiply them. And in the simplest way, how to understand attention is just multiplying matrices with each other, and that's it. So, okay, I will repeat and rephrase. We need to multiply matrix with our position here to matrices, to matrix for the other positions, for the huge context. And in the end, we will get our attention score. Like it's just multiplying. And by the way, we can see it in the code. Okay, let's continue. I think we will have one more lesson for attention, and we will go deeper to all the different ways how to calculate attention. And by the way, it's now we have more types of attention. So okay, let's move to decoder part. The decoder is responsible for generating the target sequence by using the context vector from the encoder and the attention weights. Here, the implementation of the decoder with detailed explanations, I will provide it to you. So embedding, we have embedding lower here. The decoder also uses an embedding lower to convert the word indexes into dense vectors, which serve as input to the GRU. And let's discuss how we integrate attention mechanism here. The attention weights are calculated by passing the decoder current hidden state and the encoder's output through the attention lowers. I told you in our discussions that we just multiply two matrices. And so here we have this. We calculate decoder current hidden states and encoder outputs. Just have multiplications of them. These attention weights are used to compute a weighted sum of encoder's output, which creates a context vector that focus on the most relevant parts of the input sequences. And RNN input, the input of the GRU consists of the concentration of the embedded current word, the context vector from the attention lower, and the previous hidden state. This combination allows the decoder to generate the next word in the sequence with the full context of the sentence. And the last fully connected lower, after passing through the GRU, the decoder uses a fully connected lower to generate the final output, which is a probability distribution over the target vocabulary. Okay, is it clear how we use attention in the decoder layer? We just combine what was on the previous lesson and what we created now in our techniques.
Yep, clear.
Okay, nice. So now we have defined the encoder, attention mechanism, and decoder. We need to integrate them into single sequence-to-sequence model that coordinates the entire translation process. Here we have forward path coordination, the forward method of the sequence-to-sequence model. First, encoder the source sentence using the encoder to produce a set of hidden states. Then it uses these hidden states along with the attention bytes to generate the target sentence one word at a time. Here we have also teacher forcing. Teacher forcing is a training strategy where the true output target words is fed as a next input to the decoder instead of the predicted word with a certain probability. Here we can see teacher forcing ratio. This technique helps stabilize and speed up training through it may lead to discrepancies during inference when true target words are not available. In the generation loop, here we have the target sequence is generated iteratively by the decoder. For each time step, the most probable word, or I mean token, is selected, and this word is then used as the input to the decoder for the next step. Maybe you need going through this code at home. I mean, when we will stop the lesson and maybe go into details deeper. Maybe you need to debug some code elements to understand what we are having on the at the moment, like at this code part. And here we have a lot of comments what is going on every line. I think you will get the meaning of this technique. But if not, I explained you how it's named, and you can search in the internet more details about it. Okay, so also here we'll have training loop. It's I think all of us are familiar with training loop, and we repeat it every lesson. Here we use Adam optimizer to adjust the model parameters during training. Adam is popular for its adaptive learning rates and efficient coverages. Also, we use cross-entropy loss. We always use it when we work with text because we need to work with probabilities. We need to identify on every step which token is closest for the meaning for our context. So we have like classification task, but with a lot of classes. Because of this, we use cross-entropy loss function measures how well the predicted words match the target words. We ignore patent tokens during loss calculation to prevent them from affecting the model's performance. And we have gradient clipping. Do you remember what is it? What this techniques provide?
No.
Okay, we had it on previous lesson.
Sorry, I don't remember.
Yeah, okay, so I will tell you second time. We have gradient clipping is used to prevent the exploding gradient problem, where the gradients become too large into understandable training. By limiting the gradient values, we ensure that the model converges smoothly. Let's refresh our knowledge. I provided you that example on the previous lesson. We have gradients, and maybe sometimes it's have two big values. So we just cut it. We set threshold in the beginning that our gradient value could not be higher than this threshold. If it is via our training process, we just cut it on every step where it is higher. But it's okay for us if it would be on this threshold or lower than it.
Do we have problems sometimes with vanishing gradients, maybe? Or only exploding gradients?
Can you repeat, please?
So there's also sometimes problems with vanishing gradients. A lot of models have that, but do we have it in here in this model, or only exploding gradients problem?
Exploding only.
Okay.
Yeah. It would be. No, I think in the transforming model we will have it, but here is simple way. So.
Okay.
No. Okay. Then we have evolution mode. The model is set to evolution mode using this line of code. I hope you remember it. This code line turns off dropout layers and other training specific components to ensure a consistent evolution. Also, we remember that we have teacher forcing. During evolution, we disable teacher forcing to see how well the model performs when it relies entirely on its own predictions. And also we calculate our loss function to the validation loss is computed to track the performance of the model to unseen data. Yeah, okay. Also, what we didn't discuss, we have here functions for translate sentences. We had it on previous lesson, but maybe it would be good to repeat it for the second time. So here it's just a way how we can use our implemented technique on the inference. When okay, I think we can just say that it's user-friendly interface or something like this, how we can communicate with our model. We have here tokenization. The input sentence is tokenized and then converted in the list of indexes using the source vocabulary. The tokens are enclosed with a special start. I mean SOS or EOS markers. The sentence then is passed through the encoder to produce encoder outputs and the initialize hidden state for the decoder. Then we have decoding loop. The decoding process begins with the SOS token and generates words one by one using the decoder. At each step, the decoder outputs the most likely next word, which is then fed back as the input for the next decoding step. And also we have stopping criteria. Do you remember what is stopping signal for us?
No, I don't remember.
Can you repeat, please?
No. I didn't remember. I don't remember. Sorry.
Oh, okay, so you know that we had EOS token. It's end of sequence. So when it appears in our inference, we can stop. It's a condition to stop generating process. And also if we didn't get end of sequence token, we can stop when we have maximum value, like maximum length we provided in the beginning, like a constant value. Then we stop if our predicted sequence is longer than we want. Okay, also we conversation, we have conversation tokens. We generated indexes are converted back to the corresponding words using the target vocabulary. And we have get example translation. It's here. We can see what's wrong. Okay, yeah. We provide sorry. Yeah, translate sentence and get the example translation. The function this function tests the model performance on example sentences from the dataset to help evaluate the quality of translations. And we have the function retrieves the source and target sentences from the dataset using specified index. Then it calls then translate sentence here function to generate the model's translation for the source sentence. Then it prints out the original source sentence, the ground truth target sentence, and the predicted translation. This I'm sorry. This comparison helps visualize how well the model is performing on specific examples. And it's kind of the end of code here. We had all these parts on the previous lesson. We should remember how to load state from checkpoint, which we saved on every epoch. We have it. 1 second, I will find. Yeah, we have here train functions and evaluate function, and always we save our model states. Do you remember why should we save our weights of our checkpoint on each, like on some epochs? We discussed on the previous lesson. Why should we do it? Nobody remember? Okay, I will say it for the second time. Usually we need to understand what was the best. Okay, we have evaluation part in our training process, and we need to indicate what was the best checkpoint on our training loop, on our training process, I mean. And we rely here to the best valid loss. If we indicated that it was lower than previous value, we need to save our model. Then we can use it on the inference. We can load state dict from our previous training processes and use it, for example, on production, on every task that we need. We trained it for our goal. So when we had good result, we need to use it on our tasks that on which we need to use our model. Do you remember why should we have validation data set in our training process?
Not to overfit usually.
Yeah, we need to understand validation metric on every epoch to choose our hyperparameters and we need to monitor do we have overfitting or underfitting. If you don't remember it, please watch our recorded previous lesson. We discussed it in the beginning, and it was full of examples of why should we use it, how can we indicate the overfitting process, and others information. Okay, so right now I think it would be useful to refresh why do we need attention mechanism, how we calculate attention, and all the information that we had to remember it. And on the next lesson, we will have more information about attention. We will have three ways how we can calculate it, but it wouldn't be full information about attentions, because right now we have a lot of types of attentions. We have sparse attentions and multi-head attention and other attentions. We will discuss it maybe further when we will have transformers and and other models. But right now we will discuss on the next lesson 3 types of attentions, but it would be a really important information. So, okay, motivation of attention, let's refresh it. In traditional sequence-to-sequence models, the encoder compresses the entire input sequence into a single fixed size context vector. This approach can be limiting, especially for long sentences, because it forces the model to condense all the relevant information into a single representation, which often leads to information loss. Attention allows the decoder to assess the entire sequence of encoder outputs, I mean hidden states, instead of relying on just one context vector. At each step of decoding, attention computes a weighted sum of the encoder's hidden states, focusing on the parts of the input sequence that are most relevant for generating the next word. And let's discuss how attention works. The attention mechanism computes a score for each hidden state of the encoder relative to the current hidden state of the decoder. This score indicates how important each word's its sentence is when generating the next word is a target sentence. Then these scores are normalized using the softmax function to produce attention weights that sum to 1. These weights determine how much focus the decoder should place on each word in the input sequence. And the context vector is created by taking a weighted sum of the encoder's hidden states using the attention weights. This context vector combined with the decoder's current hidden state is used to generate the next word in the target sequence. The mechanism ensures that at each step the decoder has a different context vector that dynamically adjusts based on the specific needs of the current translation step. Let's discuss why attention is critical for sequence-to-sequence models. Because attention helps the model to retain relevant information across the longer sequences, which is essential in the translation tasks where long distance dependencies can be crucial. Attention mechanism provide insights into the model decision-making process by showing which part of the input sequence influenced the output the most. And instead of using a single fixed context vector for the entire input sequence, attention dynamically creates a context vector at each decoding step based on the most relevant parts of the input. Okay, I think we discussed a lot of information about attention. Did you understand how it works? Maybe
Yes.
on the simplest example that I provided. I mean, when we have big sequence and long sequence, and we stand on each part, we can look through all of our positions that we have in the sequence and indicate is it important for us by multiplying our matrices. It's like, is it a good explanation for you, or do you need maybe read another examples from other people to understand it clearly?
I mean, so far so good. I think the explanation was good.
Okay, if you need after our lesson, I will provide you a blog post of one person. This blog post is about transformer architecture. It would be nice if you will read it and understand transformer architecture. You will need it on the in 2 lessons. But right now I will send you part where he explain attention mechanism and how does it works. I think it would be very useful for you to understand different information, how to understand it, and different ways of how to understand this mechanism. But right now, I think we discussed all of the information that I could discuss with you today.
Okay. Thank you.
Okay, thank you very much. Do you have questions?
No.
Okay, if not, we can stop our lesson earlier. And let's meet on the next week and we'll discuss more information about attention.
Thank you. Goodbye.
Thank you. Have a good evening. Goodbye.